Now, based on what we've learned so far about station components and pumps and valves, let's go into some general guidelines. And every station, of course, is a compromise between ideal pump or valve performance, automatic valve, efficiency, operational considerations, maintenance, aesthetics, and of course, initial cost. Initial cost may determine if the project should proceed, but to ignore the other station factors is exceedingly short sighted. You do have to consider all of those points. General factors, performance curve, efficiency is important, but also the slope of the performance curve. What, where the pump is going to be operating under different conditions that are liable to show up. Flow range, what is the lowest acceptable continuous flow rate and what is the highest? Inlet, need to avoid vortexing, which is air induction, and does NPSH required exceed the NPSH available? Usually that's not an issue, but sometimes. Venting, inlet pressure a factor because air compressors. So the higher the inlet pressure, the less you have to worry about venting. The lower the pressure, the more of it is a concern. Radial thrust, a factor in pump design, and similar axial thrust. Footprint, floor space required by the assembly in servicing, ease of servicing pump or automatic control valve. Number of pumps. It is both good practice and often required by regulation to have n plus 1 number of pumps, where n is the number required to meet peak flow requirements. Approach taken at one time with aircraft that basically you have one spare engine. If you had 4 engines, you had to meet performance on 3. Actually, that means nowadays, where it's common to only have 2, that they will actually outperform the older ones because you have to meet the minimum requirements with one engine of the 2 running, which means with both, you virtually have double the power available that you have to meet those minimum conditions. If peak flow can be required by one pump, then a duplex station is the simplest approach. One operating, one standby. When 2 pumps can better meet flow conditions, then a triplex is appropriate. And the majority of pumping stations are either duplex or triplex. Where you need, though, however, a broad range of flow rates, often this can be obtained by simply having a number of pumps. I've seen up to, mentioning here, seen up to 6 in parallel. And just as adjustable speed is the ideal approach for varying head, multiple pumps is the best approach for varying flow rate. Up to 6 pumps in parallel, not including, is not uncommon, and a pump discharging into line fed by other operating pumps. The one thing you have to think about, it's likely that upon pump shutdown, severe check valve slamming will occur. When you've got, say, 3, 4 pumps running and one of them shuts down, the discharge head that that pump that's being shut down sees is not going to be a case of, well, the pressure falls off and the force main nice and gentle because of inertia. No, there's almost no inertia, and you've got full header pressure, and that check valve is going to come down real quick. So you want to make sure you got a check valve that is fast closing so you can minimize water hammer. Now, using a soft state starter, which has the ramp down soft start or adjustable speed drive if it's warranted, for other reasons, can get rid of that sudden peak unless there's, well, actually with a power failure, the inertia does come into effect, so it's only in normal operation. And as I say, a soft stop can be very useful to take that edge off the slamming of one pump shutting down. Often rectangular building or above grade or below is involved. Beware below grade installations where flooding can occur with even the best of precautions. It does happen. Gravity aid should be equipped with an elastomeric deck build that will also stop rats. These are basically like the big Tideflex valve that was shown for low head applications. You get small versions of this, and they're very good at draining while preventing flooding coming back through the drain line. And as I mentioned, also very good at keeping rats out of the pump station or valve station. Ideally, electrical distribution control equipment should be located above grade, even if it requires a separate enclosure. Electric utilities will not allow, as a rule, below grade meter base, so you're going to have your primary electrical equipment above grade, and probably ideal to have your control equipment there as well. This is important. The designer should allow space for good access to all equipment, the building or chamber itself. The old rule, after careful equipment layout and sizing the building or chamber and having enough room between the pumps that you can get at them, add 50% more floor space. That is a good rule because things will get added to the station, plans change, and I've never had an operator complain that a pump station or valve station was too big. And ideally, pumps, we'll get into this further, both sides of the pumping equipment or valving can be accessed without having to climb over piping, hurdles. If a motor control center is utilized, and in many instances should be, motor control centers are a relatively inexpensive way of providing power distribution. And you can have basically a blank section for control. It is best if the electrical room provides sufficiently wide single straight wall, because MCC corners are basically lost space with them. Okay, there's nothing you can put into a corner piece, either an outside corner or an inside corner of an MCC. So the most useful is to have just a single straight run. If it is desired to isolate the electrical room from the pumping equipment with a wall, some people prefer to do that, although there's an awful lot of stations where they're not, and usually that's not a problem. But if somebody perceives it as being one and you've got them in separate rooms, there should be a decent sized tempered glass window or windows to allow direct viewing of the pumping equipment from the electrical room. Okay? And if you're going to have a standby gen set, it should be provided in a separate sound attenuated room, and again, ideally with tempered glass viewing to the electrical room. Just inside the station entrance, any header, inlet header, and the discharge header should have a master isolating valve, either non-rising stem or OS&Y gate valve, or an eccentric plug valve, if we're talking sewage particularly. So you can isolate the interior of the station simply by shutting those two valves. Each header should also include a combination air release valve just inside of that master isolating valve, so it can release air in the header and also break any vacuum if there's a shutdown, whatever, which can allow less water hammer issues. So that's a good rule of thumb. Piping should be sized on velocity, not on the sizing of the piping, never the size of the pumping connections. Occasionally you'll find that the pumping connections are big enough that they're what they should be, but in most cases you're going to have reducers and increasers. Inevitably, discharge piping, one size larger than what the discharge of the pump is. But your sizing on velocity is the way to go. An ideal line velocity of about 2 feet per second to about 8.2 for wastewater. Water pumps, if it's seen, but with water you can go up to about 13 feet per second. Done that, it is not the end of the world. Okay. The ability to prove pump flow after starting is desirable. And one way to do it is have check valves that have a position switch, such as tilting disc or flapper check for wastewater, so that you can actually tell if the check valve has opened or not. So indication of valve initial operating should be provided at the check valve end, and remote the station control panel so you can see that the thing is actually open. But basically in the controls you have it set up so like if you're starting and after a short period of time the check valve hasn't opened, and the PLC should know that, if it hasn't opened, then the pump should be stopped and an alarm provided. The pump, for whatever reason, is not working. And as appropriate, every high point where air could accumulate and cause problems should include an automatic air release valve. For example, the top of double suction split case pump casings, vertical turbine inlet barrels and discharge, both. The barrel, yes, because you'll get air trapped in there, can be a problem. I've seen it destroy pumps. For water service, these valves are compact and reliable. Appreciate with wastewater applications, even though the valve mechanism above the float, they tend to be problematic and should be used. Try to design them out as much as possible. Wastewater applications are not good for auto air release valves. Now, pump bases. A horizontal pump should be mounted on the base plate along with a coupled motor, and when you get them from the factory, they are not aligned and should never be directly installed onto a concrete pump base. I remember a case where somebody had a concrete base that was a little bit rough. The pump arrived, they bolted it down, and couplings lasted about 40 to 50 hours because you could actually, with the coupling guard off, see the misalignment that the coupling was having to deal with. So lining it up is a trick. And they, as I say, from the factory, they are not really aligned. So what you do, basically proper alignment by shimming the base plate is required, and with bolts tightened down. Coupling alignment must then be confirmed, and only when we're confirmed that the coupling alignment, both parallel and alignment and angle, is good, then and only then pour grout in to fasten the base in place. Now, the classic, you see these things about here's how you should do it. You should cast a metal sleeve into the concrete along with a bolt and a washer arrangement, such that you can then place the pump base plate onto that, wedge it as necessary, and away you go. The problem is that very often, even with the most care, it just doesn't work out. The pump base isn't, if you haven't seen it, isn't quite built the way you expected. It just becomes problematic. An alternate approach that I've seen done, and had it to the people that came up with it, is first position a base plate atop a concrete base, level, and then drill and install Hilti adhesive anchor studs before coupling. Works well near the edge of concrete because, unlike using a expanding bolt style of anchor, which actually puts a stress on the concrete, the adhesive anchors don't. And I make mention that the SkyTrain system in Vancouver, the elevated rapid rail, basically they use adhesive Hilti style anchors. Now, with vertical turbines, and this applies to any pump, we'll get it specific, you don't want to grout and fix anything permanently that may be removed in the future. For example, if you've got the discharge head, you want a stud, and studs are always nicer than bolts to work with. Studs sticking up, it's easy to guide onto. Should be mounted to a sole plate or base plate, call it what you want, and the base plate is grouted to the concrete, leveled, and then with studs, and grouted to a concrete floor. So the sole plate stays put, the discharge head can easily be removed by simply removing the nuts on the studs, and away you go. If there's an inlet barrel involved, you want to do it in two stages. In other words, again, let's start from the bottom. You want the sole plate or base plate leveled with studs and grouted to the floor. Then the barrel should slip over those studs, and it in turn have studs projecting up in order to mount the discharge head up. And of course, with an inlet barrel, that connection, as I think we mentioned before, should really have an O-ring in it so that there's no leakage. Otherwise, a gasket, but the O-ring trick works very well. Okay. Now, we're showing here there's this is for a vertical turbine. Yes, you can have a full base plate with a surrounding deal to it, almost like a horizontal pump would have, except it's intended for vertical. You can have, you notice this one, they've got a sole plate up on the top left. They got a sole plate with an earthquake resistant shear around it. What that's doing is with a sole plate is just a flat plate that you mount the pump or barrel on top of. In an earthquake, there's going to be side motion, so with this little piece sticking around it, shear resistant piece, you've got to bite into the concrete itself, and it shouldn't break loose and kick to the side. Um, and I always say studying connections is the way to go. A cheap and dirty way of doing it is if you've got a plate, rather than drilling and tapping it, what you can do is simply drill it, put a bolt through, weld the head of the bolt, tack weld it to the bottom of the base plate, and voila, you now have a stud. Valve selection, isolating. Inlet isolating valves on conventional end suction and double suction split case pumps, as well as vertical turbine pump inlet barrels or T-style heads. In other words, inlet isolating valves should be non-rising stem gate. Mounted stem vertical, is inlet flow will then remain relatively undisturbed. In other words, a non-rising stem gate valve, you got a straight through shot at the thing. Um, that's the way to do it. Discharge isolating valves should be gear operated, double offset butterfly valves, again mounted stem horizontal, disc rising. Okay, they permit the interim throttling of discharge flow for pump testing. Butterfly valves can be used, as we mentioned before, for throttling applications, and if you're testing the pump, that's good. And you say, no, my pressures are way too high. Appreciate you can get high performance butterfly valves capable of providing up to a 740 psi working pressure. Now, in fire pump applications, as I mentioned, they do use gate valves, but they use open shaft and yoke because you can visually tell if it's opened or closed. In a conventional station, probably not required. Check valves. Tilting with water. Tilting disc check valves with both visual position indicator and position switch options, which you can get to verify flow, can be considered to be the premium choice and are certainly recommended for anything 6-inch and above. The valves have to be installed horizontal, they can't be vertical. The dual disc check valve is a reasonable choice up to perhaps 4-inch. And again, as we mentioned, you have to install it with where there's an elbow so that the flow will split either side of the disc if it's off and thereby prevent any rattling of the thing. And if it's installed in a horizontal line, hinge pin should always be vertical. And we mentioned about downward flow being problematic with that type of valve. Pressure relief. In nearly all water pumping applications, a discharge pressure relief valve is advisable. These should be discharge header mounted and vented either back to the inlet header or to the source reservoir as is appropriate. The concept is you're not so much worried about shut off and pump pressure as you are situations of surges within the line. And there is, as I mentioned before, a surge anticipating valve. I am not a big fan of surge anticipating valves. They usually create more problems than they solve. And a basic pressure relief valve, properly piloted, and the ANSI standard does require that it be having a big enough relief setup that the valve will open fairly quickly. Comment from somebody, this was, what is in the States, the Corps of Engineers back years ago. In our opinion, therefore, in cases where no water column separation occurs, the most effective means of protection against pressure surges is the low inertia pressure relief valve, in other words, something that will open quick, which only opens gradually and at the required instance. This device keeps the pressure surges down to finite predetermined values and is unlikely to endanger the pipeline by causing depression waves. An additional advantage is its simple design to which it owes its reliable operation. Basically, a standard automatic control valve piloted as a relief valve will give you what you want there. And here's the bit I was going to mention that is in the ANSI AWWA standard now. Care is needed when selecting size of pressure relief pilots for the CV factor and tubing diameter because these valves will significantly impact the opening speed of the valve, particularly on large valves. You do want the valves to be able to open quickly as that pressure wave comes back. As I say, it's not going to be an instant like you get with column separation, but it will come back and it will, over several seconds, pick up fairly quickly. You want the relief valve to be able to keep up with that. A significant issue with vertical turbine pumps is the installation of the inlet barrel. Now, in industry, very often they'll put them out in the middle of nowhere, concrete pad to support the barrel at the top, and that's about it, and there they are. We tend to be a little fancier, and we'll get into that later when we're dealing with municipal water stations. Um, where you're discharging open, in other words, you're pumping to a reservoir is the classic application. Uh, that is the most efficient type of pumping because you can pump it most of the time you're pumping at a constant rate unless there's a lot of friction involved. Then you can think variable speed. Also provides a very high level of fire flow reliability. Gravity is very dependable. Uh, and while, yes, any form of kinetic pump could be used, a steep performance curve is best because differences in system head will not result in operation much away from the pump best efficiency point. And multi-stage pumps inherently do provide steep performance curves. So over at the left here, what we have is a little guide chart. Basically, open discharge. We're pumping to a reservoir. Flow is staged if we've got more than, by having several pumps. A standby, maybe you've got 3 pumps and 2 of them are doing the normal flow situation. If you're pumping from a well, suggest a submersible and coming down in purple, pancake up to about 80 gallon a minute, the small ones. Beyond that, a conventional vertical turbine bowl assembly with horsepower. I mentioned 230 is the limit with Franklin. If you're beyond that, anyway. And I would recommend adjustable speed drives so you can do that little trick of controlling the level if you try to overpump the well. Okay? And a lot of people, that happens quite often, and operators just love the fact they don't have to worry about it. Next, reservoir source. If you're pumping from one reservoir to another, then you've got pressure inlet, so you want a canned, either submersible or either vertical turbine, either vertical turbine or a canned submersible, or one of these variable multi-speed or vertical multi-speed stage pumps. Okay. Normally across the liner with soft start, if you're, we need it for both power or shutdown water hammer situations. Adjustable speed drive only if you got very high friction involved, and you can try to minimize that by playing games. If you got a pressure source, again, the vertical turbine, can submersible, or vertical multi-stage, either across the line and or solid state start. If you've got constant pressure, if you've got variable inlet pressure, then go variable speed, because that variable speed is variable head. And at the bottom, we've got all these little, so it tells you what all the things above. Okay. Now, next, well source. For deep well applications, submersible pumps are personally my favorite. Vertical turbines can be used, but pulling them from a well is a bit of a production, and well straightness, if they're long, can be an issue. In other words, the well is crooked, the pump doesn't like that. And you've got the issues of startup, pre-lubrication if you're super deep, although, as we mentioned, you can get the fancy bearings that pretty much eliminate. Air release, shutdown, vacuum brake, all of those things. The little combination, or pardon me, not combination, but basically air vacuum valve with an air throttle works very well. Going to a full deep well pump control valve, I'm not a real big fan of those. So anyway, and realize that with a vertical turbine, you're going to get well surging. In other words, the aquifer around the screen is going to get surge when the pump starts, because the pump starts with almost no head, and when it shuts down, you've got all that water in the column coming back down. Now, so I like subs. For low flows, again, up to about 80 gallon a minute, the fabricated stainless steel 4-inch pumps will be fine. You can get up to 20 horse 6-inch motors with those. Beyond this, submersible pumps using basically vertical turbine bowl assemblies, they will be significantly more efficient. And you can get 8-inch motors up to 230 horse. Those are easy to deal with. Beyond that, it becomes a bit more of an issue. Now, check valve, there are a number of different poppet styles, whatever. My personal favorite today would be, now the 4-inch fabricated stainless pumps have a built-in plate type check valve right off the bat. Beyond that, I would go there. You can get a dual disc, in other words, reasonably water hammer resistant check valve, which I consider a reliable approach, with female pipe thread specifically for this application, the Flowmatic ADSL being the only example actually that I know of. And you can get them from 2 to 8 inch sizes, and there's a picture of one. One of the things you can also do, which Flowmatic has, I'm not trying to plug. Oh, actually, they're good at it. You can get what they call a break-off plug. Now, particularly, you have to pull this pump, and there's a submersible, and there's a check valve down there. You're not only lifting the pipe and the pump and motor, you're also having to lift all the water that's in it. So what you can do is get a break-off plug option, which basically, as you can see, comes into a plug on the side of the valve and sticks out. And basically, there's a hole drilled into that. So what happens is, if you have to pull the pump, you can drop a chunk of pipe down, just an open chunk of pipe, that'll come down and hit that and break it off. Well, when it breaks off, then it starts draining, okay? And give it a little bit of time, it's all drained. Now you don't have to lift all that water. Highly suggest that there be a Lamacoid put somewhere where it says pump check valve equipped with break-off drain plug, so that people realize that weight-saving device is down there, okay? And when you're doing a check valve like that with a submersible, and the check valve is separate from the small pump than with the small pumps, then you want to have one length of pipe, a random length, and random lengths are around 18 to 20 foot. You just order them as a random length. Should be installed between the pump discharge and the check valve. That way, any sliming of the check valve is dampened somewhat before the shock wave hits the pump itself. And discharge riser pipe check valve should be sized so that the maximum operating velocity will not exceed about 10 feet per second. Okay, there's some initial guide points, and we'll go on to more in the next issue.